Hello, everyone, and welcome back to your channel of Math and Engineering Made Easy. So today I'm going to start probability, and then the next session we'll do statistics. I have like a review sheet here on probability problems. I printed like 16 problems. I think we can do only half of them. Make the calculator handy. So if something needs explanation, I will do it along the way. So it's not like I'm not going to do a session on talking about probability. And as I said, I have a whole playlist of probability and covers this stuff and more. So you can even consult that if you need. So you can look at the first few sessions there that discuss what you cover in Algebra 2. Um, so let's not waste time and start right away. So if we look at problem number one, I'm going to read it if it's not clear on the screen. It says a bag contains hair ribbons for a spirit rally. The bag contains 5 black ribbons and 7 green ribbons. Just that, right? 7 and 5. Lila selects a ribbon at random. Then Jessica selects a ribbon at random from the remaining ribbons. Find the probability that both events A and B occur. That Lila selects a black ribbon, and event B, Jessica selects a green ribbon. Okay, so that's event A, that's event B. Notice that these probabilities, we call them like um, you can think of it as in the beginning, we had 12 ribbons, 5 plus 7, and Lila wanted to select one of the 5. So she had, since the ribbons um, are in the bag, they are likely, each one of them is having the same probability of being selected as any other, right? We are not going to look into the bag and select the color we want. No, they are shuffled, randomly, and we just pick one. So the probability that Lila picks a 5 if she has 12 identical ribbons except for color, the probability that she picks one is 5 out of 12, right? Whether she gets it or not, now the bag contains only 11 ribbons. All are likely have the same likelihood of being selected. But now I have 7 green ribbons out of 11. Why 11? Because Lila already picked one. Whether she picked a black or a green, there is only 11. So now the probability is 7 over 11. And to find the probability that both occur, and because these two are independent of each other, meaning they have nothing to do with each other, right? So I multiply them. And when I multiply 5 times 7, I get 35. 12 times 11 is 132. And that's basically number C. That's pretty straightforward. Okay, number 3. It says a movie company surveyed 1,000 people. So the N of the survey is 1,000. 229 said they went to see the new movie on Friday. See on Friday. 256 said they went on Saturday. If 24 saw the movie both nights, so 24 Friday and Saturday, what is the probability that a person chosen at random saw the movie on Friday or Saturday? So what is that? Now, when we say that, this is important, by the way, guys. Okay? When we say Friday or Saturday, in the context of probability, and this is it's not it's not clearly written. I don't like the way it's written because when we talk our language, like English language, natural language, day to day, when you go to a restaurant, they ask you, for example, uh, how do you want to start? Do you want a soup or salad? We call that the exclusive or, meaning if you select soup, they don't expect you to select both. Yeah, of course, you can say, no, I want both. But the order, usually when it comes, they give you a selection of either one. And we call that the exclusive or, meaning if you select one, we exclude the other. But in probability, when I say two events, this or that, I mean inclusive. We call it logical or, not day-to-day or. This or is inclusive, meaning either A or B or both. What confuses some students is that if I have a sample space and then I have two events, this is A and this is B, and we say the probability of A or B, we write it the probability of a event A or B. We say it's the probability of A plus the probability of B minus the probability of A and B. And they say, no, we are subtracting, so it's exclusive. It's still inclusive. Why? Because when I say, if I call this area area number one, and this area number two, and this area number three, the probability of A is area one plus area two. The probability of B is area two plus area three. So when I subtract the probability of A and B, I'm subtracting one of these, but still the other one is included. So probability of A or B is this whole area. And the reason I subtracted, this is not a guy with two eyes. Okay. The reason I subtracted is that the area number two, which is A and B, was counted twice, not because it's exclusive. If I want to say probability of A exclusive or X or B, I have to subtract this one twice because I added it with A and I added it again with B, but I don't want it. I want exclusively A or B. So I would have to subtract this twice. Okay, just to confirm that. So now the case we have is this number is 1000 instead of probability, it's number, it's fine. The whole A, which is Friday, is 229. So the numbers included in all of that is 229. And the number inside that is 256. And the number in the middle is 24. So if I say the probability of A, assuming this is event A and this is event B, and I'm sorry, or B, the probability of A or B, it's the probability of A, which is 229 over 1000, plus the probability of B, event B, which is 256 over 1000, minus the probability of A and B, minus 24 over 1000, equals over 1000. 29 minus 24 is 5. So this is 205. So that would be 461, meaning the probability is 0.461. Do we have that? Yeah, C. So it's also C. Okay? Notice, because if these numbers are large and you have a large interaction, you may end up, when you add the numbers, to get a probability of more than 100% if you don't subtract these the quantity in the middle. But we subtract it once and it's still inclusive, as I said. Events A and B are independent. Find the missing probability. If the probability of A and B, if you have two independent events, we say the probability of A and B equals the probability of A times the probability of B if and only if A and B are independent events. Notice there is a big difference between independent and exclusive, mutually exclusive. Mutually exclusive meaning they don't have anything in common. So you have one like here and one like there. Okay? So these two can never be independent. They are mutually exclusive. Those may be independent. How do I know? If I say the probability of A and B equals the probability of A times the probability of B. And vice versa. If I know they are independent, then I know that this equation is there. So what do they give me? A and B are independent. So they say the probability of A and B is 0.06. And they give me the probability of B as 0.3. And they want to know what is the probability of A. So of course, the probability of A would be 0.06 over 0.3 equals 0.2. So it's, oh my God, all the ones we selected were C. Okay. Let's move to the second page. Next one is number 7. Of 50 students going on a class trip, 35 students are athlete. So these are 35. And 5 are left-handed. Of the student athletes, 3 are left-handed. So there is 3 here, which means 2 left-handed students are not athlete. Do you see that we can just write it like that? And then out of these 35, 32 are not left-handed. So basically we have 30, and then, oh, I'm sorry, of 50 students going on a class trip, 35. So basically what I have is my sample space has 50, okay? 32 are athlete right-handed, 2 are two-handed, left-handed, but they are not athletes, and 3 are left-handed athletes, which makes the sum 38. I'm sorry, 37. That means there are 13 students who are right-handed, but not athletes, which are outside of that. So if I can make another rectangle, I would place, so now I don't need those because they are inside, and outside there are 13. So they tell you what is the probability that one of the students on the trip, if I select one at random out of these 50, is an athlete. So if I call that event A and this is event B, what the probability that I have A or B, either athlete or left-handed or both. So what is this probability? It's easy. We know that 13 are out. So what's inside are the 37 that are either athletes or left-handed or both. Notice, or in probability, unless stated exclusive, that it's an exclusive or, we assume it's inclusive. So the probability here is this plus this minus, so this, which is 35, plus this, which is 5 minus 3. So you get 37, which are the sum of these 3, right? Divided by 50 because they are 50, meaning if I multiply top and bottom by 2, I get 0.74. No, get out of here. It's also C. What is wrong with this thing? And of course, they want you to get 40 over 50 or zero point 0.8, so they put it as one of the choices, but it's not correct because now you will be counting the left-handed athlete twice. Once with athletes, once with left-handed, but it's the same person. Why do you count them twice? You go to number 9. The sections on a spinner are numbered from 1 to 8. If the probability of landing on a given section is the same for all sections, so they are, oh, that reminds me of a story. I have to tell it. I'm sorry. I was in high school, in middle school, in ninth grade, um, because in Egypt we have 633. So the ninth grade is the third, like the third year or the last year in our middle school. And then we had like a dancing party in, we were an all male student school, and there is an all female school that had like an end of year party, and usually they invite us to go. So we went there, and there was a spinner. They are playing a spinner with three areas, but they were not equal. So it didn't take a genius to understand that the likelihood that you get on the larger portion. So I selected the larger portion and I thought everybody will fight with me on it. And no, the other people used the smaller ones. And I had a lot. I won. I was like, I had the so I won, and then unfortunately, I don't drink. And even if I do, at the time, I was a middle schooler. And the funny thing is that they had like a bottle of beer as the prize. And I said, oh my God. Now, the peer pressure. I looked around and, the people were waiting for me. So I grabbed it and they said, but you don't drink. I said, who told you that? I drink, of course. And then I opened it and I couldn't. Oh my God, I didn't like it at all, but I had to take sips in front of them until they moved and then throw it away. But I remember when it says spinners of the same size, that's what you expect, right? But this one was amazing. It's like two-thirds were one block, and then the other third was divided into two small pieces. And nobody objected when I picked. I don't know why they did it like that anyway, beyond the point, but it's funny. So what is the probability of spinning a number less than 4? Okay, so there are 8, okay? Less than 4, notice, word is very important. When I say less than, I don't include the 4. If I say at most 4, then the 4 is included. Or no more than 4, the 4 is included. But if I say less than 4, it means 1, 2, or 3. Or greater than 7. Well, there is only a greater than 7 is 8, right? It's not at least 7, in which case 7 and 8 would be included. No, greater than. Less than and greater than, meaning the 4 and the 8 are not included. So now I have 4 areas. What is the probability that you get that? Well, they are all 8, and I have 1, 2, 3, 4. 4 out of 8 is 1/2. And finally, we get something that is not C as the answer. Okay? Last page, number 12. Let's look at that. What is number 12? Oh my God. No, I'm not going to do 12 because it's a spinner is divided. It's the same thing. Let's do 9. I don't know why they give the same. Anyway, let's do 13, 14, and 16, for example. I don't know. Even though this seems to be similar to the previous ones. 13. A person is selected at random. What's the probability that the person was not born on a Monday? Express your answer as a percent. If necessary, round your answer to the nearest tenth of a percent. Well, there are 7 days in it. There are 7 days, okay, in a week. So if the person is not born on Monday, then this person has 6 chances out of 7 to be born on. So you get 6 divided by 7 is 0.85 something. So it's 85.7. That's also a very easy one. Um, should you do 14 and 16 or 14 and 15? Because I think this is very similar to the previous one. Let's look at 14. What is the probability of rolling a 5 on the first number cube and rolling a 6 on the second number cube? Assume the number cubes are fair and have 6 sides. Express your answer as a fraction in simplest form. This is funny. It says rolling rolling 5 on the first number cube is 1 out of 6, right? And rolling 6 or any other number in the second is also 1 out of 6. And since these two events are independent, meaning if I tell you I rolled the first one and I got a 5, what is the probability that I get a 6 on the second one? You say, are you crazy? What does that have to do? What what do these events have to do with each other? Whether you get a 5 or a 1 or a 2, the probability that you get a 6 on the second is still 1 out of 6. They are not related. And because of that, we say they are independent. And here we said if they are independent, you multiply the probabilities. So out of 6 times 1 out of 6 is 1. I'm not continuing. I give up. It's C, 1 out of 36. Guys, please don't use C if you don't know the answer, as many people will tell you. But that's usually when you have 5 choices, right? They tell you if you are in doubt, pick C. Why? Okay. At a school carnival, one of the booths has 12 plastic ducks floating in a tub of water. Each duck has either a 0, 1, or 2 printed on the bottom, indicating the number of prize tickets you receive if you select that duck. 6 of the ducks have a 0, 3 have a 1, and 3 have a 2. If you randomly select a duck and then randomly select another duck without returning the first, what is the probability that you will receive 4 prize tickets? 0, 1, and 2, and you are going to select twice. So the only way you can get 4 prizes is that you select a duck that has 2 written on it, and then select another one that also has 2. There is nothing else. If one of them has 0 or 1, you're lost. You cannot get 4. So the probability that you get 2 from the first trial, and since you have only 2 printed, I'm sorry, you have 3 ducks with a number 2 underneath. So the first trial is 3 out of 12. Then the next time you select, there are only 2 ducks with 2 on them and 11 ducks overall. So times 2 out of 11. I subtract 1 from here because I already selected the first one. It has a 2. So only 2 ducks have 2 written on them. And since I select 1 out of the 12, only 11 remain. 6 over 12 is 2, so this is 1 over 22. Yes, B. I think they make C only for the odd ones. No, this is odd. Okay, I think that's enough. Um, so it wasn't bad. Maybe we can do 16 since it didn't take that long. Of 100 workers in a stadium. So again, you can draw the space and it has 100 in it. 42 work in the concession. So I'm going to call that event A. And A has 42. And 88 are wearing name tags. That's B. Of the workers in the concession stand, 6 are wearing name tags. 6 of the 42. meaning 35 are wearing name. So it has both. And only 7 are here. And since all of these are 88, so those uh, the rest of the people wearing name tags, but they don't work in the concession is 88 minus 35 or 53. And since those add up to 95, there are 5 people who neither work in the concession stand nor are wearing name tags. So now we made it so clear. They tell you which is the probability that one of the workers is in concession or inclusive or wearing a name tag. So this plus this divided by 100. These were 88 already, we know that. Plus 7 is 95 divided by 100 is C again. Do you see how we did it? We broke them down. And then notice that if you say, for example, what is the probability of A or B, and you forget to subtract this, you would say the probability of A is 42, the probability of B is 88 out of 100. When you add them, you get 130. What? So the probability is 1.3? You told us there is no probability greater than 1. Yeah, because there are people that you counted twice, which are these 35. So they are not 130, they are 130 minus 35. 130 minus 30 is 100, minus another 5 is 95. Okay? I hope this clarifies the idea of independence or mutually exclusive, or why do we subtract the middle part? We don't subtract it because they are exclusive. They are still inclusive, but we counted them twice. If you want to make them exclusive, so if I tell you, what is the probability that a person either works in the concession stand or wearing a tag, but not both? Then I would say 53 plus 7 is 60. It's 0.6, 60% chance. I subtracted 35 twice. When I subtracted that once, I got 90, 95. When I subtract it again, I get 60. Okay? I don't think they will ask you about exclusive because we usually don't go over that in the course, but I want you to understand why that if we want exclusive, I would subtract the the intersection here twice. Okay, I hope it wasn't that bad. I don't know. I think I did a couple of 2 or 3. I can't remember today. So if I'm still awake, I don't want to, give you wrong ideas. So if I'm awake, I'll do the last one on statistics, and so we can complete the course with trigonometry in the remaining few days. As I said, I already started posting 2 videos a day, so I can cram the whole course and give you time to study for the Regents, which I hope you nail it down. Okay, if you have any questions, as usual, feel free to comment, send me a comment. Otherwise, I wish you all the best. I hope to see you soon.